Okay, I'm really grateful for the opportunity to participate in this wonderful meeting. I think we've had good discussions and we've not been shy about asking each other naive questions, which is always good. I have got 4 little stories I'd like to tell to you today. I really don't mind if we only get through the first one. So please just butt in if there's anything that you'd like to go off on a tangent about. It's absolutely fine. Before getting started with that, I want to introduce a number of co-workers who worked on the things I'm going to tell you about, together also with some of the people who've paid in order to make it happen. Okay, we're going to look mostly at the electronic structure problem, and like previous speakers have done, I'm going to try in a moment just to give you a sketch of where that is, what the main things in play are. Although if we get that far, I want to tell you a little bit actually about how you can do quantum mechanics with both electrons and bosonic particles. Okay, so here's my slide on how we set all this thing up. We're talking about electrons in molecules. The Hamiltonian is always written in a basis of orbitals, 1 electron functions. There are typically 20 of those per atom in the molecule. So the number of those functions, let's say, is a few thousand in a typical chemically useful molecule. The Hamiltonian is defined by these 1 and 2 electron integrals, and these operators P, dagger, and Q are the usual second quantization operators, or if you prefer to think about it, provided we're not changing the number of electrons, it's always an annihilation followed by an excitation. So P dagger Q just replaces orbital Q with orbital P in whatever it's acting on. Okay, the domain of that operator is the set of Slater determinants, as we've already discussed. So what is that? We can make products of those 1 electron functions. There are going to be very many of them. Instead of just the simple products, we'll have those that have the anti-symmetrization operator applied to them. Those are what we call the Slater determinants. As previously discussed, the size of that space is absolutely huge, and we have to find approximations. The first approximation is a mean field approximation. That's Hartree-Fock, where we just take 1 Slater determinant, and then, of course, we simply minimize its energy variationally to give us a set of what the chemists would call molecular orbitals, optimum orbitals. That orbital picture, Hartree-Fock picture, is actually what is discussed by every chemist. The way they talk about molecules is firstly about molecular structure. Well, that needs the Born-Oppenheimer approximation. And secondly, they like to discuss what orbitals are involved in any change that you want to consider. And that's resting on this single configuration Hartree-Fock picture. And we have to ask the question, and we're going to look at the question, what's missing? And the thing that's missing is that the electrons see each other, so to speak, in real time. They follow each other's tracks. Their motions are correlated. Whereas in the mean field approximation, then they just see the average field of the other electrons. Unfortunately, the electron correlation is significant. Energetically, it's about an electron volt per pair of electrons. And that is on the chemical energy scale because the strength of a chemical bond is roughly 3 electron volts. So we have to be a little bit worried as to whether or not the mean field picture is or is not going to be able to solve the particular problem that we're interested in, because its errors are certainly on its absolute errors at least are certainly on the order of the energy scale that we're working with. In principle, we could do what we call full CI to construct the complete space of Slater determinants, but as we've seen before, this is just huge and we're not going to do it. We're always going to approximate. Right, here is just a little bit more to talk about how electron correlation manifests itself in molecules, and I think there are 3 things that are going on. The first is that the Hartree-Fock picture doesn't work when you break a chemical bond. So what's shown on the left-hand side there is a wave function for dihydrogen. 2 electrons are put into this orbital, one with alpha spin, one with beta spin, that is the in-phase combination of the 2 atomic orbitals. And that has an energy that's lower than the atomic orbitals because of interference, kinetic energy. But when you pull the molecule apart, it becomes degenerate with the atomic orbitals and the out-of-phase antibonding combination. So at dissociation, there are two Slater determinants which are equally important. If you just take the Hartree-Fock Slater determinant, it gives you a mixture of atomic states which include the ones you want, where there is one electron on each of the hydrogen atoms, but also includes contributions where you've got two electrons on one atom and none on the other, ionic states, which is just unphysical. And you can solve that problem by mixing in a little bit of the other configuration where we put two electrons in the antibonding orbital. And with the right mixture, then the ionic contributions cancel, and you're left with the so-called covalent ones. So that's telling us that electron correlation is important when you get near degeneracies, which happens when you break chemical bonds. And the way to solve it is by doing what we would call configuration interaction, which is variational calculation, usually involving just a few of the Slater determinants that are important. Okay, so that's one aspect of correlation. The second, on the right-hand side, is the so-called dynamic correlation. So what we're looking at there is a potential energy curve for the molecule F2, the ground state energy as you stretch the bond. And the right answer is in red. If you do Hartree-Fock, you get the black curve. It not only goes to the wrong dissociation limits, for the reason we just discussed, but also its energy is far too high. And the reason for that is what is usually called dynamic correlation, and it's associated mostly with the shape of the electronic wave function as two electrons come close together. There's a singularity in the Hamiltonian because of the Coulomb operator, and therefore the wave function must have a particular shape so that the kinetic energy, which is the Laplacian acting on the wave function, will exactly cancel the Coulomb singularity. And that shape is a cusp. You can see it there. The blue curve there is the exact wave function for helium in some cut, and the red curve is what Hartree-Fock gives you. Hartree-Fock doesn't see this electron-electron coalescence because the electron moves in the average field of the other electron. It never sees it actually. So the naive interpretation is that Hartree-Fock overestimates the probability that the two electrons come close, so the potential energy is too high. There's more going on there because you can perhaps see that the kinetic energy of the exact wave function is going to be more than the kinetic energy of the Hartree-Fock because it's more wiggly. Okay, and well, I think we don't need to discuss further, but the potential wins. So that's so-called dynamic correlation, and if you think about it, that's going to be in every molecule. It turns out that approximately 1 electron volt per pair of electrons is involved there, and so in this difluorine case, what's happening is that in the molecule there are 9 electron pairs, but in each atom there are 4 electron pairs. So you're losing 1 electron pair, and that means that the size of the correlation energy has changed. If you don't break a chemical bond, then although you have this absolute error, then you may get cancellation of that error as you just move atoms around in the molecule. And that's indeed why Hartree-Fock can be said to work. The other thing that's related is the van der Waals dispersion interaction. 2 argon atoms are not bound in the Hartree-Fock method, but they are bound by electron correlation. Okay, this is a map of the families of computational methods that are used for dealing with electron correlation effects, and we're going to just visit bits of this in the rest of the talk. So the first thing you can decide is whether or not the thing that we had on the left-hand side of the previous slide is in play or not, whether we've got strong static correlation. If we haven't, then you can use perturbation ideas in order to introduce the correlation. You can ask the questions, what Slater determinant should I mix in to get an improvement of first order? And the answer is that you can mix in just those Slater determinants which have 2 electrons changed. This is arising from the two-body nature of the Hamiltonian. And one way of thinking about doing that is to make a wave function which has the Hartree-Fock plus some set of double excitations like this acting on the Hartree-Fock. And you can variationally minimize the energy of that, but it's not a good idea because it leads to energies that don't scale correctly with the number of electrons. You need a wave function actually that's multiplicatively separable to give energies that are additively separable. And so what you actually do is what we call couple cluster theory, where instead of 1 plus t, we do e to the t, and then you can probably easily see that that's going to give you separability, and a little bit of further consideration, you can see that the energy is going to be rigorously extensive in the electron number. So that's One family of methods that we can pursue, and we'll talk a bit more about this later. Actually, most of the effort in my career has gone on something completely different, which is where we have strong static correlation and we try to deal with that at the outset. I don't want to talk too much about it, but there's a whole family of multi-configurational reference methods where we start with not just one Slater determinant, but some linear combination of them in order to get the dissociation problem correct. And then we think about the dynamic correlation afterwards. The third family of methods are those where we don't try too hard to do the quantum mechanics from first principles of electron correlation, but seek some kind of model. So I'm going to offend some people by classing density functional theory and density matrix functional theory in those terms. Usually, most practical density functional theory certainly is using some functional that is parameterized and parameterized on empirical data, and that's a good way of bringing in the dynamic electron correlation that is in nature, provided that, of course, that parameterization is somehow reasonable and likely to be global in its validity. And in fact, in density functional theory, you may know that really the effect of this is it adds an effective additional potential that each electron moves in a pseudo one-electron picture. It's a very simple theory, a little bit like Hartree-Fock, but with a different potential. Okay, so now let's move on to the first story. And this is about exploring coupled cluster theory and addressing the question as to whether or not it can do more than just do the dynamic correlation in a molecule. Could we use it instead of multi-configurational methods for dealing with bond breaking and maybe excited states? Okay, well, does it work? Here is a potential energy curve for the dinitrogen molecule. It's got 3 chemical bonds, 3 sets of three bonding orbitals, and as you pull the thing apart, the kind of grey curve there is a close to exact potential energy curve, and the red is what you get with coupled cluster theory at single and double excitations. And it's clearly things are not working well in that region as you go out to dissociation. Okay, so it's not quite adequate. The normal way, we need to talk a little bit about how coupled cluster theory is done. The normal way is to take Schrödinger's equation with the coupled cluster wave function and then simply project that against a suitable space. And so that's what you're seeing here. Actually, for technical reasons, we also pre-multiply by this e to the minus t to make an effective Hamiltonian that's a similarity transformation of the original Hamiltonian. And then we project that. These Qs are the operators that generate orbital excitations, electron excitations, that we have in constructing the wave function. So they define a space onto which we can project, and the energy we can get just by making this expectation value across the reference state. But it's not the only thing we could do, and indeed there are possible disadvantages of this approach. We've got a Hamiltonian here that is now non-Hermitian. We've not got an energy minimization problem. Okay. Another thing we could do is simply take the coupled cluster wave function and evaluate the expectation value of the Hamiltonian operator and just minimize that with respect to the parameters. That would be so-called variational coupled cluster. If the set of excitations up here were complete, involving single, double, triple, all the way up to n-fold excitations, then those two approaches would actually be the same, and they'd be equivalent to solving the full CI problem. But of course, the interest is in not having a complete set of operators, but in truncating it. And when the operator manifold is truncated, then the projection coupled cluster and the variational coupled cluster are not the same thing. And we're going to expect differences that are significant when the correlation is strong. In other words, when the operator itself is large, the coefficients in it are large. Well, everybody uses the traditional projection coupled cluster and nobody uses the variational. Why? Well, in the similarity transfer Hamiltonian, what it gives you is, if you use the Baker-Campbell-Hausdorff expansion, this, in principle, infinite series of exponential, it terminates at fourth order, because it involves a commutator expansion, and you run out of things to couple to each other after the fourth index. And so you end up with a set of quartic equations, not infinite order, okay, in the projection form. But unfortunately, this doesn't work in the same way with variational, and the exponential expansion has to, in principle, go on forever, or until you believe that you've done enough in order to stop. So nobody uses it. However, of course, many of you will be aware of a related method to variational coupled cluster, where you parameterize the wave function with a unitary transformation, which we can do with e to the t minus t dagger. That's actually very similar to variational coupled cluster. They agree to, I think, fourth power in the t operator, and the obvious utility is, of course, for quantum computing. This is a way of propagating a state with a unitary transformation. So there's a revived interest in unitary coupled cluster. Okay, one way to find out is just to do numerical experiments to find out whether it will be worth doing variational coupled cluster. So here is a numerical experiment. This is a calculation on dinitrogen, which is not related to nature in the sense that we've used a very small orbital basis set for which we can solve the Schrödinger equation exactly, full configuration interaction. So this includes just actually the important valence orbitals in dinitrogen. And the curves aren't very clear, but the exact potential energy curve is somewhere in this mess here, and this is what you get with projection coupled cluster. Okay, it just diverges as you go to infinite bond length. And it shouldn't take you long to realize that if you do variational coupled cluster, this can't happen because the energy is a true upper bound to the exact energy, and therefore it can't go below it. So you can't get that divergence as you go to infinity. The plot on the left is just the same thing, but differences to full CI. You can take this further and do not just single and double excitations, but triple and quadruple, and it's the same story, but the energy scale is of course much smaller. CCS-DTQ is already very good, but variational CCS-DTQ is much better. Okay, you can see that 0.95 instead of 14.01 millihartrees error when you stretch the bond to twice its equilibrium value. So that's telling us that there's maybe some potential to do variational coupled cluster theory or an approximation to it as a way of handling the static correlation problem at the same time as the dynamic problem without having the complication that I haven't discussed but which is there of multi-reference methods, which would be the normal way to do it. So here is a way to do it. The problem with variational configuration interaction is that you have a Rayleigh quotient which has a denominator which is the norm of the wave function. And that means that you have an inhomogeneous expression for the energy that can't possibly scale with the number of electrons. What's going on here is that energy denominator is effectively replaced by multiplying the numerator in that expression with a matrix quantity, a matrix inverse, which keeps the connected tensor property of the whole thing. And you only collapse to a scalar at the very end. So that gives you an energy functional which is guaranteed to be extensive simply because of the connectedness. And one can set up, I don't want to discuss the details, one can set up a practicable theory which does that, and in fact it agrees with variational coupled cluster in up to third order in the series expansion of this exponential. These four Feynman diagrams come in, and they agree exactly with variational coupled cluster for those diagrams, and also reproduce the two-electron problem precisely, and so on and so on. So that's what we call quasi-variational coupled cluster, and I don't want to show you too many results because I think that that's not of such interest in this audience. But here is, again, dinitrogen, but this time with a much... Yes?
I got a question about, I don't speak diagrams fluently, but so can you, like, where does it go, like, haywire? Like, where does it go south with the traditional coupled cluster in terms of the diagrams?
So traditional coupled cluster does not have this with the same coefficient.
Ah, so they have the same diagrams, but the weights are just different.
Some of the same diagrams, yeah. I think.
So what I understood from coupled cluster is that, sure, they're wrong, but it's so manyth order, you're going to be correcting those?
Yeah, but you'd need to include the triple and quadruple excitations in order to get to the right answer. So It's hard to discuss because there are very many diagrams.
Yeah,
when you
exactly.
go beyond this.
But variational has it correct at, there's no like cancellation or correction in higher order?
Of course, at the next order, variational doesn't have quasi-variational doesn't have the right diagrams, doesn't have all of the right diagrams because they're too expensive to compute. But for 2 electrons, it works exactly. A lot of those other diagrams just happen to give 0 when you have only 2 electrons. Triple excitations do nothing when you've only got 2 electrons, for example. Okay, the quasi-variational with some additional correction for triple excitations is that blue curve there, which is sitting next to the black curve, which is what you get with multi-reference methods, which is basically the truth. So it doesn't always come out that way, but it provides a substantial improvement and gives something which we can use for problems with strong static correlation.
Can I ask, so this O stands for orbital optimized?
Yeah, you have to optimize the orbitals.
How
Yeah,
crucial is it to orbital?
you have to do. Of course, you have to do it. There are no single excitations in this theory, so you have to do orbital optimization instead.
But then it adds to the complexity and cost.
You have to do it, but it's not
Okay.
it's not the biggest part of the cost. Okay, now when you maybe you've had this experience of having an idea and finding that it works quite nicely, and then along comes your friend who has an idea which looks wrong but works much better. So here is one, and this distinguishable cluster approximation, Katzenbambi, is a little bit like what I just showed you, except they have deleted one of the diagrams. There's a diagram there which has the Coulomb part, but the exchange part has been thrown away. And there's a rationale for that, that in the strongly correlating limit, this can give you the right answer. But of course, it's not physical, okay, because electrons are fermions, and you can't just throw away exchange. And what should we look at here? This is a kind of study of performance on a chemical problem, and their thing is this DCSD, which has an error for the barrier height for the reaction of 2.6 kilojoules per mole. If you do CCSD, it's 5.5. And if you do the thing I described to you a moment ago, it's also not so good, 7. And many other problems where it actually gives you surprisingly good numbers. Okay. We decided to have some fun by looking at the numerical solution of the equations that govern any of these methods, actually. So the couple cluster method, that's a quartic equation in the amplitudes, nonlinear equations, polynomial equation, and it's going to have very many roots. Some of those roots, the number of roots might be larger than the dimension of the underlying Hilbert space. So some of them might not be physical, or they might be. And so we decided to look at this in actually a very naive way. You can, of course, explore the roots of polynomial equations, how they disappear into the complex plane and all of that when you change parameters using Grubner base theory or whatever. We just did the very simple thing of doing numerical experiments to look for as many solutions as possible of these equations. And we did it for a very simple example, just 4 electrons in 4 orbitals. For a case where there's strong electron correlation, that's 4 hydrogen atoms in a square. It's a case where Hartree-Fock doesn't work because it has an energy which you can simply work out, which has a contribution that scales with the size of the square to the power -1. That's indicative of ionic interactions. And of course, this square will just simply dissociate into 4 hydrogen atoms in reality with no Coulomb interaction between them. And the exact energy is -2, -0.5 for each hydrogen atom, asymptotically. So at the separated atom limit, all pair theories are going to be fine. And what matters is what happens when the 4 electrons come close and we've got correlation between all 4 electrons. And here's what you can get if you do, first of all, couple cluster theory with single and double excitations. Actually, the single excitations don't come in for symmetry reasons. So what are we looking at? On the bottom, the pink dotted line is the three of them are the exact Schrödinger states, the solutions of the full CI problem, as you stretch this hydrogen atom square. And the blue line that you see there is the CCD ground state, and you can see that it's pretty faithful, gets quite close to the exact. It's a little bit below it, it's not variational. And you can also find some other roots of the couple cluster equations which come at high energy, and at least one of them actually corresponds to the first excited singlet state in some way. You could believe that that's what goes on. If you do variational couple cluster, this time the ground state is a little bit better. Actually, it has to be above the exact energy because it's variational, and it's a little bit closer than the projection couple cluster. And again, you can find a small number of excited states, again, some of which may mimic the physical states. There's always the caveat that I've not found all of the solutions, okay? Because this is just a numerical experiment, not an exhaustive search of all of the polynomial roots. If, however, you do this distinguishable cluster approximation, then all hell breaks loose. And you find very many solutions of the equations, one of which is extremely close to the exact energy, but the others are, of course, all unphysical, and many of them corresponding to energies which are very low indeed. And if you were to find one of those, then that would be a catastrophe. Fortunately, with the equation solvers that we have, we normally start from the weakly correlated limit, so your chances of finding the physical solution are pretty good. You don't often run into this kind of trouble, but it's disturbing to know that those problems are there. Okay, let's now shift to story number 2. Yes?
For the last picture, so you found one which works well, right? This I understood in this picture.
Yeah, down here.
But there are the other solutions, and can you jump from a good to a bad solution, or by is?
Can you appreciate that finding all these is numerically is tricky, right? Because a little bit of noise and you jump to another solution.
Or if you start a little bit to the right, you could have hit a green one instead of.
I mean, these were all found by shooting from the right, of course. You can prepare solutions in the asymptotic limit that you know what they look like.
Or you go backwards.
And you can see my poor drawing here, that vertical line is a jump.
If you read from the right, you don't know whether you hit the right one at all.
You don't know whether you hit the right one, that's correct. Although actually you do, because you can look
at... but that danger is there, right?
Yeah. But you can prepare all the others and just follow them in.
Wow, okay.
I think there are many more solutions than I've shown you. Right? Because my mathematics isn't enough to find all of them.
And you have to start with the picture at some point.
Yeah.
That's very helpful.
Right, let's carry on. Topic number 2. This is a very old problem, and the idea is to avoid doing couple cluster theory, but to do a simpler theory where we use perturbation theory to look for electron correlation. And this can give you an electronic structure method which is the cheapest possible that introduces electron correlation. And it's a series, perturbation theory, Rayleigh-Schrödinger perturbation theory gives you a series, and what you want to do is to truncate that series at low order, because you don't want to calculate the higher order terms. And you should immediately ask the question, does the series converge rapidly? Because otherwise truncation will be meaningless. And the secondary question is, does it converge at all? Or is it an asymptotic series in some sense that you can use? Okay. It's difficult to do analysis on this because the Hamiltonian has just got numbers in it, and lots of numbers, but you can do numerical experiments. And these are the numerical experiments that we did 40 years ago, where we use the apparatus of solving Schrödinger's equation exactly in a small basis set, and then also solving the perturbation equations in that basis set. So because we've got the complete Hilbert space, we can follow the perturbation series out to infinite order without writing complicated programs where each order you have a different set of diagrams to include. Okay? It's just a numerical thing. Okay, the numbers are too small to see, but this is those 40-year-old experiments where you look at the contributions order by order to the correlation energy of the water molecule at its equilibrium geometry and at some stretch geometries. And if you follow what I said before, the stretch geometries, the correlation is going to be stronger. And the numbers are in Hartrees, and the chemistry is at the third decimal place. So you can perhaps see that close to the equilibrium geometry, we're kind of done at fourth and fifth order, but at longer bond lengths, we are not done. And there may indeed be divergences. Okay, let's discuss the convergence a little bit. The second order energy looks like this thing on the bottom right-hand side. We start with the eigenfunctions of the Hartree-Fock one-electron Hamiltonian as our unperturbed problem. And we can then construct the second order correction to that is just the usual Radius-Schrödinger form with these energy denominators. So there's an obvious thing that if you've got a molecule with a near degeneracy, low-lying anti-bonding orbital, then that energy gap is going to be small, and you can expect trouble with a perturbation series. Okay, you can expect it to converge slowly. And the jargon that's often used is that that's a front door intruder, a state that's going to just cause the perturbation series to diverge for obvious physical reasons. But there's more. You have to look in the whole complex, whole unit circle in the complex plane in order to establish the convergence. And for the neon atom, which is electronically hard, there are no, it's not easily polarizable, there are no low-lying excited states. For the neon atom, there is trouble. And the trouble comes because the spectrum of the zero-order Hamiltonian, the first excited state, crosses with the ground state when, in perturbation theory, we've got a Hamiltonian which is the H0 plus a lambda times the difference between. So if that lambda is negative and near the real axis, you get a crossing in the spectrum. And actually on the real axis, you get a very close to crossing. It's avoided. There's a small imaginary part to the value of lambda where this crossing happens. So that tells us that the series is going to diverge, right? That we've got these points somewhere in the unit circle in the complex plane. You can see it's actually close to the edge of the unit circle because that's -1 there. And if we change the Hamiltonian slightly, which we can do by changing the basis set, you can actually make that point go outside the unit circle, and then you get convergence. Okay, there's another kind of problem with perturbation theory, which is all to do with static correlation and spin contamination. Actually, I'm not going to discuss it. We've not got time. Let's just kind of summarize where we've got to so far. We are working with this zero-order Hamiltonian, which is just the Fock operator, the effective one-electron Hamiltonian for the system in the Hartree-Fock mean field picture. Okay, now this is a bit of a peculiar way of setting up perturbation theory. The normal thing with perturbation theory is you have a hydrogen atom, and then you switch on an electric field. So you have the hydrogen atom without the field, you know it's Hamiltonian, and then what is the electric field? It adds a little bit to the Hamiltonian, and that's your perturbation. In this case, we know the only thing we've really got is the full Hamiltonian for the full system, and the perturbation theory is just made up. There's no physical object, there's no physical thing which is the zero-order problem. What we have to do is to look for a zero-order Hamiltonian for which the Hartree-Fock is the exact eigenfunction. Okay, and then we can go ahead and construct perturbation theory. And we want that Hamiltonian, that zero-order Hamiltonian, to be somehow close to the exact Hamiltonian. Okay, so the sum of the Fock operators is the usual way of doing it. Then every Slater determinant is in fact an eigenfunction of that operator, because all of the orbitals are eigenvalues of the one-electron operator. And we can easily construct the energy denominators as we need to. But this isn't the only thing we could do. We can, in fact, have an H0 which has different numbers in it. And the requirement actually is that there should be nothing in the matrix, in the block of the matrix, that connects the occupied orbitals with the unoccupied orbitals. That should be 0. That's something called Brillouin's theorem. It's equivalent to the variational condition for the Hartree-Fock. but we can play around with the occupied blocks and the virtual blocks, and this was indeed noticed by Ernie Davidson a long time ago. So what we're going to do is play with the zero-order Hamiltonian to see whether we can get something where this h0 plus lambda h1 varies only slowly with lambda. All right, so we don't get these crossings, if we can avoid it, within the unit circle in the complex plane. Chooses different h0s so that somehow the spectrum, the electronic spectrum, is only varying slowly with the perturbation strength parameter. We want, however, that H0 is still a one-electron operator for computational cost reasons, but this is a one-electron operator. Okay, so what do? We set up a zero-order Hamiltonian. There it is, as I described on the previous slide. And we want to make it such that H0 acting on the first-order wave function is as close as possible to the exact Hamiltonian acting on the first-order wave function. That's a way of making those operators as similar as possible. And in order to do that, we just need to project onto a suitable space and get a set of linear equations which are going to determine these parameters lambda in the virtuals and lambda in the occupieds. And that's it. Okay, we call it perturbation-adaptive perturbation theory because we're determining the zero-order Hamiltonian from actually the perturbation itself, rather than being some independent thing that already exists. Okay, let's skip that. And we're going to skip the practicalities, except to say that, again, I'm going to do the same thing of exploration, where we use full configuration interaction technology to take this to whatever order we want. But in the end, the idea is that we will deploy this using Optimum software. And it's actually the same as, once we've found the Hamiltonian, it's the same software as we use to do Muller-Plesset perturbation theory at second, third, and fourth order. The only thing that's different is the zero-order Hamiltonian, its eigenfunctions and its eigenvalues. That's all that's different. Okay, so here is an example of the front door intruder, a molecule where there's a physically identifiable low-lying excited state. This is singlet methylene, CH2. There's a low-lying orbital, and we can make a double excitation from the highest occupied molecular orbital to the lowest unoccupied molecular orbital, and it's relatively low energy. The black curve there is regular Muller-Plesset many-body perturbation theory, and this is showing now the error in the truncated sum of the series as a function of order. It's very slowly convergent. Remember that chemistry is roughly here. Okay, so we're in trouble if we want to truncate this at low order. Here is now the same thing with the new Hamiltonian, the perturbation-adapted perturbation theory, and the convergence is, again, regular, much more rapid. And in particular, we've got an advantage at low order that mean that we can use this method. Here is the same thing for the neon atom. So again, the black is Muller-Plesset perturbation theory. Because of that backdoor intruder, you get these oscillations as you go up in order of perturbation theory. The errors are alternately plus and minus, and they grow as you go to high order. It's the same thing, actually, with the new zero-order Hamiltonian, but the effect is much smaller, and the divergence comes much, much later. So it's an improvement. Okay, we can actually do some chemistry with this and see whether it works. So here is an example of a database where the dissociation energy, some reaction energies are known from experiments, and you can compensate for all the other possible errors except electron correlation to get an effective empirical number. And what we're looking at here is how this works across this set of about 15 molecules, and I can't remember how many reactions. These are statistics showing the spread of the errors relative to zero. CCSD parenthesis T is the conventional coupled cluster with perturbative correction for triples. CCSD is coupled cluster theory without that correction. So to do chemistry, you need the CCS3 parenthesis T. And the result is that at second and third order, this new perturbation theory is basically as good as coupled cluster theory, and certainly much better than second and third order Muller-Plesset perturbation theory. And if we go to fourth order, then it's actually very close to coupled cluster theory with triple excitations with a significantly reduced cost. We don't need to discuss that. It works also in other situations. This is binding energies of non-covalently bound complexes, weak interactions, which are of course important to get right when you want to describe chemistry of large molecules. And again, this is now the difference with coupled cluster with triple excitations, and those differences are pretty small. At third order, it's a little bit better actually than CCSD, even though it costs much less. Okay. Yes.
Question about that. So this same problem of diverging denominator, you of course, as you know, we also have that in metals.
Yes.
And how about your...
Yeah, so I wanted to,
does
actually,
that work for-
one of the things I'm trying to do with pencil and paper is just do this for the uniform electron gas, which is hopefully is relevant to the metal, sufficiently close. I haven't got there yet. But one would hope that there's a gap. But I really don't know. Because, of course, the exact Hamiltonian has a gap in the spectrum, can have a gap in the spectrum, depending on the... I guess it doesn't for the uniform electron gas. But maybe you might not get the divergence, because the... Yeah, I'm not sure.
Yes, so in the total energy you can avoid the divergence.
Yes, yes.
For example, by summing the RPA diagram.
So those divergences are cancelled by terms in different orders of perturbation theories. It's a little bit tricky. And I guess that cancellation, it would still need to be done like that. So my guess is it'll still diverge. I'm not sure.
Probably. I mean, there's another way of getting around the problem by using for H naught, not Hartree-Fock, but the exchange-only OEP.
Yes, yes.
Because then for the uniform
Yeah.
electron gas
Yeah.
having local potential,
Yeah.
it's just the plane waves, right? So,
Yeah.
And so the problem is gone.
And maybe this would do a similar thing to the OEP somehow. It's worth a look. Yeah. Good, thank you. So actually, we've got 10 minutes left. I'm going to offer you a choice out of the last two topics. So there's this, which is just a little bit of nonsense, actually, about density matrix functionals in the same spirit as the exploration I showed you of coupled cluster solutions. And the other thing I can show you is to look at electron-boson interactions in quantum mechanics. Which do you like best? We can't do both, I think.
Are you voting or?
Vote, well, just the noisiest person will determine it, probably.
Electron vote or?
Bosons. Bosons. Okay, bosons it is. If you want to, so what kind of physical systems are we thinking of? The way we got into this was to find another way of looking at non-adiabatic processes, where the Born-Oppenheimer approximation is not good. So the normal way of doing that is to start with the clamped nucleus Schrödinger equation and find not just the ground state, but several excited states, and then include the coupling between those that comes from the nuclear kinetic energy operator. Now, if you've ever done that, it's a pain in the backside. It's not a nice thing to do. And it's a strange thing, because you start with a two-body problem with a Coulomb operator, and you turn it into an n-body problem by making this potential energy surface. And the nuclear motion problem is more difficult than electrons, actually. So another way to do this would be just to treat the electrons and the phonons together. Why not? Okay. The other thing that we started doing then was to think about systems where you have electrons and, let's say, photons, but really a molecule in an optical cavity, where there are some quantum modes in that cavity which can couple to the electrons with a Hamiltonian that I'm going to show you in a moment. Okay, and maybe you know that there are many people doing experiments with this, trying to control the properties of matters by resonances or whatever with this cavity. Okay, so what we're going to see actually is just a first exploration of that for simple systems, unfortunately not for the molecules that people put in the cavities, because they are big and there's lots going on. Okay, now you can perform a trick to avoid thinking about the boson quantum mechanics at all in doing this particular problem. Not every boson problem, but this one. And the trick is, well, maybe Ove Christensen invented it, but I'm not sure whether it comes from earlier. We can make a basis set for the boson modes. So, for example, for vibrations, this could be the set of harmonic oscillator functions, or it could be something else. It doesn't matter, really, as long as it's a complete basis. And then we can imagine exciting the system. There are no bosons here, right? These are just wave functions for the vibration. We excite the system from the ground state to the excited state to the second excited state. And we'll deal with those excitations alone. And we can make operators that do those excitations from the vibrational or cavity ground state to these higher excited states. And they are actually the same thing as the boson creation operators. That's what they do. Okay? We can then pretend that these are the states of a fermionic system. And the reason we're allowed to do that is because we only ever have one particle in this pseudo mode. Right? So the statistics don't matter. Anything involving the exchange interaction will cancel. And this means that we can use the same program that we use for electrons to do the bosons, or indeed the whole problem where we've got the two together. Okay? And we have some operators which are like the excitation operators we have in electronic structure theory, which, you can see what it is. It just...
Why is it only one particle?
Well, because, there isn't a particle there at all. This is just a construction. And all you have are the states for the vibrational mode. So there's a pseudo-particle that you're exciting from the ground state into these excited states. That's the idea. And you can write the Hamiltonian in terms of these operators.
So this is then tied to the harmonic approximation?
No, not at all.
Well,
not at all. Well, it is...
Harmonic, follow-on interactions. So you have at least two.
But they come in the Hamiltonian. They'll come in the Hamiltonian eventually. But defining the space, this is fine. Because the space, if you had two vibrational modes, then you'd have one set like this for one vibrational mode, one for the other, and then you've got a product space to define all of the possible vibration. I think you cover the full space.
Did you check the anti-commutation relations with the tau operators?
Sorry?
Did you check the anti-commutation relations with the tau operators?
Well, anti-commutation, it doesn't matter. You can use anti-commutation relations, and for the reason I said there's only ever one particle in this mode, there's no consequence. You could use commutation relations if you wanted to. The same diagrams can be used.
So flipping between 1 and 2, for instance, like creating the two.
So you could describe that by you could jump from 0 to 1 and then from 1 to 2, or you could jump from 0 to 2. The operator will do it fine. And there's a de-excitation operator as well. You can visit the whole space. You may need a product of more operators than you would need. So, for example, Eugene does this problem using bosonic operators, and there may be an advantage because you need fewer operators to find a highly excited state. But this is simpler. Okay. Yeah.
It's still a bit of a mystery. So if you start with a full Coulomb Hamiltonian of everything.
Yeah.
So where do these guys then come into play?
You should read this paper. It's all made up. It's all made up. But it has the effect of generating the states, the basis states that you need. And it gives you an algebra you can then work with that looks the same as the fermionic algebra. Exchange never comes in because you only ever have one particle occupied. So you can imagine there are, with electrons, you have two sorts of particles. You have alpha spin electrons and beta spin electrons. And the alpha spin electrons are identical to each other and have fermionic statistics. The beta are identical to each other, have fermionic statistics, but there's no exchange between the two. We're now adding a third kind of particle, which is motion in this vibrational mode, or this cavity mode. And the wave function will then be the Hilbert space will be all of the alpha spin products, all of the beta spin products, and all of the instances of each of these states here, which is just one-dimensional for each mode.
In the full electronuclear Hamiltonian, you don't have vibrations in the first place. You need to make...
What are we doing? We're transforming from coordinate space into function space, all right? We're using a basis set to go from first quantization to second quantization. That's what we're doing.
Sure.
Yeah. And I think you do cover the whole space, and it's described in more detail there. Okay, what does the system look like? We can have a molecule which has got a ground state and some excited state, and then modes of the cavity, and sometimes we will get a resonance or near resonance between these, and we will get what a physicist will call a polariton, which is a strongly coupled mixture of an electron with a cavity mode. Okay? And it's that we're looking for. We're pretty clear on what the Hamiltonian is for just the cavity bits. It's just harmonic oscillator. We're pretty clear on what the Hamiltonian is for the molecule, and we just now have to look at the coupling. And for the coupling, you can, as many people have shown, just look at what comes from quantum electrodynamics in leading order, and there's an operator which has the electronic dipole together with the, basically this is the position of the, A deca plus A is just the x coordinate. And there's also a diamagnetic term, which is that electronic dipole squared, which is benign but shifts the energy. Okay, what we're looking at there is the photoabsorption cross-section of a simple model, which is a 4-electron Hubbard system, and it's done with various kinds of theories. So the x-axis is the natural frequency of the cavity, omega c. The y-axis is the frequency of a laser field that you apply. And there are going to be some diagonal lines, which are going to be the resonances then of the laser field with the cavity. Okay, we expect to see the dark color means we get absorption. We're also going to get some horizontal lines, which are the excitation between electronic states caused by the laser coming into resonance with the electron excitation energy. And if we have no coupling switched on, this is doing the electronic problem exactly. That's all we see. If we do now full configuration interaction for the whole of the space, outer product space of electrons and cavity, then now you see both those cavity states, diagonal lines, and the electronic states, and of course they cross, or rather have an avoided crossing, which is when you get resonance between them. And the point of this picture is that we can do coupled cluster theory. We have to play around with the levels of excitations that we get. We can do coupled cluster theory, which gets most of, but not all, of that detail of the crossing of the ground and excited states.
Can you tell us whether d hat is an operator or a number? D hat.
It's an operator acting on the electronic coordinates. It's the same operator you use to work out the dipole moment of a molecule. It's just the position of the electrons, actually. This is very easy to set up software for, because the only thing you have to really care about is getting the Hamiltonian right and injecting the integrals of this coupling Hamiltonian. But then we can just use a coupled cluster program and equation of motion coupled cluster that finds the excited states that works for electrons. We don't have to do anything new. And let's just look at an example, and I'll shut up. Of course, carbon monoxide is not a candidate for being a molecule in an optical cavity, but it's a prototype that we can just look at the effect of the coupling. And what we're going to look at is the rho vibronic spectrum of that. So each of the electronic states will have vibrational states in it, and we can, if we do optical spectroscopy, then we'll see the resonances between those. And what are we looking at in this potential curve? Here is the ground state. Here is the electronically excited state. And then here is the electronic ground state with the cavity excited state. So it's just shifted up by the cavity energy. And because the electronically excited state and ground electronic state are not parallel to each other, then we're going to get a point, we're going to get the possibility that these two excited states cross, and around here we'll get the strong resonance that gives you the polariton. Right? And there are lots, the curve is busy because it's shown for different values of the coupling strength in the Hamiltonian between the photonic part and the electronic part. So you could calculate the spectrum then, and the first thing you might try and do is use the Born-Oppenheimer approximation, but actually we haven't got time to look at the detail. It turns out you can't really just use the Born-Oppenheimer approximation, because as you go through this strong coupling regime, the nature of the electronic nature changes strongly. So you have to do a non-adiabatic calculation, and when you do that, you get a spectrum which is perturbed, but not too much, from the cavity-free spectrum. Okay, I think it's time for me to shut up. Those are the 4 things I showed you, and I've enjoyed the discussion very much and happy to continue it.